In this active circuit designed using two ideal op-amp, we want to show that Vout, that is shown here, is related to Vin, that is the input voltage applied in this circuit, via equation 10 times delta, in which delta is the parameter for the four resistors shown in this configuration. Okay, to do that quickly, then focus on Vn. Vn is applied at the positive input terminal of an ideal op-amp that is in the non-inverting formation. Let's make the assumption that the supply voltage is positive negative supply voltage of op-amp properly applied, and as you can see, negative feedback is properly in place for both op-amp, and therefore as a result of that we can make the assumption that both op-amps are in linear region of operation. Because of that, I can make simple assumption that virtual short is valid for both op-amp, which means the voltage at positive input terminal of each op-amp is equal to voltage at negative input terminal of each op-amp. For example, that means when Vin appears at V positive, therefore Vin should be at V negative as well. So this voltage here is Vin. And as a result, the voltage drop across R is Vn because it is grounded. So if you have another R, since the current that is flowing through these two resistors is the same current, because nothing can go through the input terminal of the ideal op-amp. Therefore, as a result, across 2R in series, the voltage drop will be 2 times Vn, since across 1R is Vn. So here is 2 times Vn, and because no current can flow through the input of ideal op-amp again for the second op-amp, therefore, there is no current that is flowing through this resistor, so there is no voltage drop. So if here we have 2 Vn, therefore, here we also have 2 Vn as the voltage. And as a result, this second op-amp as well, virtual short is valid for the second op-amp. So if the 2 Vn appears at the positive input terminal, 2 Vn should be at the negative as well, which means this node. So here is 2 Vn. That's the beauty of this circuit. For those who are interested to sort of recall the non-inverting configuration, this first set, you have at positive input terminal, we have Vn. At negative input terminal, we have a feedback resistor R going to the output, which is, let's say, this node, Vx. So at the output, you can see Vx, and then there is this this resistor R. Let me see if I can, yes. There is this resistor R that is connected. So there is this resistor R that is connecting this one. So I am showing it here. And then there is the resistor R that is grounded, AC grounded. So this is, and this is Vx. So for this non-inverting formation, it is well known that Vx is 1 plus feedback resistor. So I mean this resistor here, and then divide by the other resistor times the Vin applied to the positive input terminal, which obviously means Vx is 2 times Vin, which is exactly what I intuitively said it is. Okay, now that we know this node, let me change the color. So now that we know this node is 2 Vn, we can compute this current I, because nothing can go or nothing can come out of the negative input terminal of an ideal op-amp because it has infinite input impedance. So this current is 0. Therefore, whatever current I is going this way is the same current I that is going through this resistor. Let's compute it. I is equal to 2 times Vn divided by the resistor that is going through it. So it's R. Okay, so let's keep this as equation 1 because it is very useful. Now, this current I is coming out of these two branches. Interestingly, one branch on the left side, you can see the sum of the series resistor is 5R times 1 plus delta plus 5R times 1 minus delta, and when you add them together, the result is just 10R. For the right branch, there are two resistors in series, and with the same logic, you can see that the sum of these two resistors in series is also 10R. So the lesson learned is we have two right and left branches in parallel with the same amount of resistance. Therefore, if the total current that is coming out of them is I, half of that current going through the right branch, half of it going to the left branch. So this current is 0.5I, and this current is also 0.5I. Great. So if I name the voltage here as Vy, then I can compute Vout given the polarity that is defined for Vout. So I'm gonna just compute it in one shot. I can say Vout is equal to Vy, and then to get to positive voltage, I have to subtract the voltage drop across this resistor here. How much is the voltage drop? Is 5R times 1 plus delta, 1 minus delta, 1 minus delta, times 0.5I, the current that is going through it. So that's, with this, I got to positive terminal of Vout. So this is Vout positive. And then I need to subtract the negative. So that is, again, as you can see, Vy minus voltage drop across this resistor this time to get to the negative terminal of Vout. So it's going to be Vy minus 5R, this time 1 plus delta, and 0.5I. That's it. Okay, great. So let me change the color so that we have a little bit more contrast here. All right then, so what am I getting at? Okay, so let me just say, as a result, I get Vout equal to this Vy and Vy cancel out, so I get rid of both of them. So these two guys cancel out. What remains? It's I get negative 5 times 0.5, so I get negative 2.5 IR, 1 minus delta, and I get, be careful of this negative, and then another negative, so plus 5 times 0.5, so 2.5 IR, and 1 plus delta. Great. So if we just simplify things, the nice thing is this 1 and this 1 cancel out each other because of this negative and positive. So what remains is simply 2.5 IR delta times 2. So this becomes as simple as 5R, and I'm going to use equation 1 that is shown here to substitute I. So I'm going to substitute this I with 2V in, divide by R, and delta. I already took care of multiplying 2 with 2.5 and I wrote 5. So R cancel out with R, and as a result I get exactly what I wanted. I get 10 times delta V in, which is exactly what was the desired equation from the beginning of the problem. I hope that this example is helpful.